So I want you to close your eyes for a second. Just imagine a standard physics simulation.
Like the kind you'd see in, well, maybe a high school science class.
Right, exactly. Or, a digital model of a chemical reaction. Usually when we picture those atoms, they're acting like blind, perfectly rigid little billiard balls.
Yeah, just mindlessly crashing into each other.
Bouncing off in random directions based on whatever they immediately hit. But the sources we're diving into today ask you to throw that mental image completely out the window.
They really do. It's a massive shift.
It is. Because instead, I want you to imagine that every single atom in a physical simulation, as if looking up at the night sky, bathes in the relative velocities of light rays from all directions.
It's such a profound shift in perspective. You have to realize that an atom isn't some closed-off, independent little sphere.
Right. It acts like a tiny camera eye.
Exactly. It functions almost like a photon sail out in deep space.
Yeah.
I mean, just as a physical sail catches the solar wind to propel a ship forward, an atom catches this continuous 360-degree rain of light from the entire universe.
Wow.
And its very existence, its behavior, its physical state, it's all determined by the relative velocity of those incoming rays.
Okay, let's unpack this, because we are talking about fundamentally rewriting the physics engine of reality here.
We absolutely are. So our mission for this deep dive is to completely dismantle the way modern physics and, honestly, computer simulations view space and time.
Which is usually just these abstract mathematical grids, right?
Yeah, exactly. For over a century, traditional models have relied on these perfectly rigid grids to explain how things move. But the documents we're analyzing today argue that we need to walk away from those purely symbolic math equations.
And move toward what?
A real-world physical construction.
Yeah.
A universe where information delay, like the actual literal time it takes for a ray of light to travel from point A to point B, that delay dictates absolutely everything.
Okay, so to understand why an atom needs to act like a camera eye, I think we first have to realize that our normal everyday view of reality is, it's kind of a massive illusion.
Right. The sources actually call it the rigid body illusion.
Which sounds like a sci-fi movie, but it's just about how we see objects. Like, think about a large object, say a city bus driving past you.
You tend to assume that the bus you're seeing is keeping its rectangular shape simultaneously from all viewpoints.
Right. You assume that what you are seeing right now is exactly how that object exists in this exact microsecond.
But the speed of light is finite. It takes time for the light bouncing off the back of the bus to reach your eye.
And slightly less time for the light bouncing off the front of the bus to reach your eye. Because, well, the back of the bus is physically further away from me than the front.
Exactly. So you are never seeing the bus as it is right now. You are seeing a mashup of past information.
That is just mind-bending to think about.
I know, right? The further away a specific part of an object is, the older the information reaching your eye. But classical Newtonian physics completely ignores this delay.
Right. Newton operated from what they call a God's eye view.
Yes, his mathematical models assume this massive, absolute space where you could essentially pause the universe and know where everything was simultaneously.
It assumes instantaneous action at a distance, as if gravity could just act with zero time delay across millions of miles of empty space.
Which doesn't actually make physical sense when you factor in the speed limit of light.
Right. It's like building a physics theory by pretending you have a magical fast-forward button. And because traditional physics operated on this magical assumption, it caused massive headaches when scientists actually tried to measure the speed of light.
Which brings us to the famous Michelson-Morley experiment in the late 1800s.
Right. They built this device, an interferometer. It shot light beams in two different directions, bounced them off mirrors, and then brought them back together.
And the goal there was to see if the light beam traveling in the same direction the Earth was moving would be slowed down by the so-called wind of space.
But when they ran it, they couldn't detect any difference in the light's speed, right? No matter which way they pointed the device.
Exactly. And to explain this away, physicists came up with something called Lorentz contraction. They claimed that space itself mathematically shrank the physical device just enough to make the speed of light measure the same.
Which is just a purely abstract mathematical fix.
Yeah, it was a symbolic Band-Aid. But our sources propose a radical, purely mechanical alternative to space magically shrinking.
Okay, let's cut the picture of what physically happened during this experiment, because the sources provide some genuinely wild details here.
Oh, the specific numbers are fascinating.
Yeah, so let's say this interferometer device was moving through the electromagnetic field at a massive speed, like 60% the speed of light.
Right, 0.6 C.
The person running the experiment would literally have to turn knobs to adjust the length of the metal arms holding the mirrors. They'd adjust them until the light patterns, the interference fringes, matched up perfectly clearly on their screen.
And to achieve that perfect clarity at that high speed, they couldn't just use a perfect circle. They had to manually tune the machine into a squashed elliptical shape.
Like stretching the device vertically. So it had a y-axis length of 20 and an x-axis length of 16. It was significantly longer in one direction.
Now here's the critical mechanical part. When they rotated this entire squashed device 90 degrees to take another measurement, the physical arms didn't stay the same length in the grid.
Wait, really?
Yeah. As the device spun, the arm that was pointing forward physically shortened, and the arm pointing sideways physically lengthened.
So the coordinates physically changed.
Exactly. The distances between the mirrors literally swapped proportions, like shifting from x equals 8, y equals 0, to all of a sudden being x equals 0, y equals 10.
Wait, hold on. You're losing me a bit here. Are you saying the metal atoms in this brass machine are somehow, like, aware enough to shift their spacing just because the machine is turning? Because if it's not space magically shrinking, like traditional physics says, how is that not magic on the part of the metal itself?
That's a great question, but it isn't awareness at all. It is purely mechanical thermodynamics.
Okay, how so?
When you move any physical structure through a dense medium, forces act upon it. The device is a dynamic physical system made of atoms held together by electromagnetic bonds. As it rotates through the electromagnetic field at high speeds, the pressure on those atomic bonds actually changes.
Oh.
So to maintain its lowest energy state, the entire atomic structure imperceptibly shifts and deforms.
Okay. So it's more like a biological system, or honestly, even just a water balloon.
A water balloon is a perfect analogy.
Right, because if you push on a water balloon, it dynamically rearranges its shape to maintain a stable pressure so it doesn't pop. So the interferometer is just deforming in the wind to maintain physical equilibrium.
Exactly. And that equilibrium just happens to be the exact shape where the light patterns look clear to the observer.
That makes so much more sense. It's a mechanical self-correction.
It is. But because physicists misunderstood this internal mechanical atomic deformation as the external space itself shrinking, they built completely flawed mathematical models.
They built a symbolic fairy tale.
Right, instead of looking at the real physical construction of the event.
And because traditional physics got trapped in this mathematical fairy tale, the author of these sources argues we need a completely new framework for how we model space. Which brings us to something I find really fun: video games.
Yes. Specifically, the sources say we need to adopt a first-person shooter, or FPS, model of reality.
Which sounds completely absurd for theoretical physics.
This sounds unusual, yeah.
Yeah.
But it forces a level of rigorous realism that classical math just lacks. To fix this symbolic world, the author argues that classical physics acts like a lazy stage
A
director.
stage director.
Yeah. Imagine a director who just waves a wand, points to a spot on the empty stage, and says, "Let there be a chair at coordinates XYZ." And instantly, the chair is just calculated into existence.
Right. Instantaneous spawning. There's no travel time, no physical construction.
But in the real world, you can't be a stage director. You have to be a construction worker. You have to physically haul the raw materials to the site. It takes time. There is a delay.
And to illustrate this, the sources lay out this really specific FPS simulation cube to explain how a physics model should actually be built.
Let's visualize this cube for everyone.
Yeah, so imagine a 3D grid in a computer program, right? A 20 by 20 by 20 grid.
Right. Now, in classical math, the origin point 000 is just an invisible, abstract center of the room.
But in this FPS model, the origin is not the abstract center. The origin is literally the camera eye. It's the observer.
Exactly. The physical reality of the observer becomes the absolute anchor of the entire universe. Rather than placing the camera in the middle, the text describes pulling the camera eye way back into the bottom corner of the grid looking inward.
So the camera sits at like -8, -8, 8.
Yes. Meanwhile, the right hand, the active element doing the actual construction or bringing in materials, is reaching out from the opposite upper corner at 8, 8, 8.
And it gets even more detailed. It maps out the physical depth of the observer too. There's a monitor plane, basically the screen you're looking at, situated a short distance in front of the camera eye at y equals -10.
But the actual real physical body, like the observer's shoulder sitting back in the chair, is anchored far behind the monitor at y equals -100.
This whole setup reminds me so much of Albrecht Dürer's perspective drawings from the Renaissance.
Oh, that's a brilliant connection.
Yeah, because Dürer didn't just mathematically guess how a lute or a person should look in 3D space. He built literal physical grids with string.
Right, he mapped it out practically.
Exactly. He'd pull a string from the surface of the object, through a wooden frame on his table, right to a fixed metal hook on the wall. And that hook represented his eye. He meticulously mapped the physical, point-to-point path of the light.
And what's fascinating here is that this specific geometry enforces the fundamental law of near action.
Meaning you can't just spawn things far away.
Right. You cannot simply spawn an object in the distance and pretend it instantly interacts with the observer. You must calculate the physical time it takes for the light of that object to traverse the space between the far corner of the room and the camera eye.
So in this model, observation is not some passive math equation. It is an active physical event that requires time.
Because the speed of light is finite, there's always a delay. C equals 1 delay. There's a gap between the event happening and the camera eye registering it.
Dürer was doing exactly what modern physical simulations fail to do. He was respecting the actual physical journey of the information.
Yes. And now, if we understand that observation relies entirely on the literal delay of light reaching a specific camera eye, we have to scale this logic down.
We can't just apply it to humans looking at screens.
Exactly. We must apply this exact same logic to the microscopic level.
And this brings us right back to the hook we started with. If we apply this FPS model to a physics simulation with its strict rules about delayed light and near action, every single atom becomes its own camera eye.
Which is completely wild. Currently, if you look at molecular dynamics simulations, they just show atoms bumping into each other locally. They only react to immediate physical proximity.
But if an atom is a camera eye, it's not just sitting in a dark, empty box only caring about what it bumps into.
Not at all.
It is looking up at the night sky. Like we said earlier, every single atom is bathed in the relative velocities of light rays from all directions, exactly like a photon sail bathing in light.
Every star, every planet, every other atom in the universe is radiating information at it. And because the speed of light is limited, the atom is catching rays of light that have been traveling for milliseconds or years or even billions of years.
That's incredible. And the texts introduce a really fascinating term for this state, right?
Yes, they call it an atom's mood, written in Japanese as kibun.
Kibun.
This is a vital concept. An atom's physical state, its momentum, and its energy aren't just about local collisions anymore. Its mood is defined by the sum total of the relative velocities of all the delayed light rays hitting it from the entire universe at that specific exact moment.
The photon sail analogy really makes this click for me. A sail in space doesn't just move because it has an internal engine. It moves because millions of photons are physically striking the fabric, transferring momentum.
Exactly.
So if an atom is bathed in relative velocities from all directions like a photon sail, then matter itself isn't really a solid thing, is it?
It really isn't. The author actually calls matter an entropy-based phenomenon. It's not a collection of isolated, rigid spheres floating in an empty void. Matter is continuously shaped, maintained, and physically constructed by the universe's light information raining down on it.
Okay, let me push back a bit here, or at least clarify. If I apply this to something massive like gravity or planetary orbits, does that mean the Earth isn't pulled toward where the sun actually is at this exact second?
Yes, that is exactly what it means.
Wait, really? It's pulled toward where the sun appears to be based on the delayed light arriving at the Earth's camera eye?
You've got it. The Earth only knows where the sun is based on the information that has physically reached it.
Right, the light delay.
Because light and gravity travel at the same finite speed, there's an 8-minute delay. The Earth's atomic mood is reacting to an 8-minute-old sun.
Yeah, it is just... Wow. But wait, if everything in the universe is just reacting to delayed light from other moving things, how do we ever establish what is actually moving?
Ah, that is the big problem.
Because if atom A is looking at atom B, and both are moving, and the light between them is delayed, it becomes a total paradox. Like, if I'm on a train looking at the tracks, and you're on the tracks looking at the train, we can argue forever about who is stationary and who is in motion if we only use each other as reference points.
The sources refer to this as the trap of two-party relativity. Einstein's framework often traps us in this very dynamic where everything is relative only to the observer.
Which leads to all those weird mathematical paradoxes.
Exactly. So
Well-
to break out of it, The texts argue we must introduce three-party relativity.
Mm-hmm.
We have to introduce the medium itself, the physical electromagnetic field that fills all of space as the third party.
The text gives two really powerful visuals for this third party. The first one is a Wimbledon tennis umpire.
I love this analogy.
Yeah, imagine the umpire sitting high up at the chair above the court. Two players are running around hitting the ball. The umpire receives two tennis balls, which represent photons in this scenario coming from completely different directions. Because the umpire is a fixed third point, receiving the balls from both players simultaneously, they serve as the point of integration. The umpire physically anchors the relationship between the two moving players.
And the second visual the text uses is even more tangible, the Wilson cloud chamber.
Oh, right. What exactly is that again?
They're these glass boxes filled with supersaturated alcohol vapor. When a high-energy subatomic particle shoots through it, it ionizes the vapor, leaving a literal, physical trail of clouds.
And the text uses this really striking image of an orange cosmic ray piercing through the chamber.
Yes. Consider how that orange streak of plasma functions. It physically burns a line into the vapor medium. It leaves a tangible scar.
A mark in the actual medium.
Exactly. And if we connect this to the bigger picture, that orange cosmic ray acts as an absolute physical anchor in the room. By measuring an object's movement against that physical scar left in the medium, rather than against another moving object, you can separate an observer's rotation from actual true forward movement.
Because you aren't relying on abstract math comparing two floating objects anymore. You are comparing them both against a fixed physical mark in the ocean they are floating in.
Yes. You've broken out of Einstein's trap.
This circles right back to the fatal flaw of the Michelson interferometer we talked about earlier.
It absolutely does.
Yeah.
The interferometer failed to detect movement because it relied on a round-trip light bounce.
Right. The light went out to the mirror, fighting upstream against the spatial wind, and then bounced back, riding downstream.
And mathematically, that round trip perfectly canceled out the delay, completely hiding the movement through the medium.
But the text brings up an astronomer from the 1700s, James Bradley, and his discovery of stellar aberration.
Bradley's work is crucial here.
Bradley realized that to see a star clearly, he had to slightly tilt his telescope forward. Think of it like running in the rain with a bucket. If you hold the bucket straight up, the rain just hits the side.
Right, it doesn't collect.
But to catch the rain at the bottom of the bucket while you are running, you have to tilt the bucket forward into your path. Bradley was essentially catching the rain of starlight.
By doing this, Bradley was measuring a one-way trip of light against the medium. He didn't bounce the light back. He just caught it.
And that one-way catch revealed the Earth's true motion through space. He was treating his telescope exactly like the camera eye in our FPS model, catching the delayed light from the night sky.
Okay, let's summarize where we've been today, because this completely upends how we picture reality.
Yeah, we've covered a lot. We started by dismantling the rigid body illusion, that false idea that we see the world instantly, and the flawed assumption that space magically shrinks to make our math work out.
From there, we moved away from abstract mathematical coordinates into a visceral first-person shooter reality. A universe where observation requires the literal physical delay of hauling information across a grid.
Which led us to the realization that every single atom in the universe acts like a camera eye. They aren't solid billiard balls. They are photon sails, navigating a sea of delayed light, their moods constantly adjusting to the relative velocities of the rays hitting them.
And finally, we realized that the only way to measure true motion in this sea is through three-party relativity, measuring one-way trips of light against the fixed medium itself.
So why does all this matter? What's the application here?
The practical application of this is immense. If we start building next-generation physics engines, video games, and AI simulations using this camera eye paradigm where every particle calculates the delayed light hitting it, we might finally unlock simulations that naturally manifest relativistic effects.
Wow, so you wouldn't have to artificially code in gravity or light speed limits?
Exactly. The system would generate them organically. We'd be moving from drawing a cartoon to growing a digital universe.
It is a total paradigm shift. So what does this all mean for you, listening right now? Well, consider the implications of the mood of an atom. If the atoms making up your physical body are not permanent rigid things, but rather continuous events shaped by the delayed light arriving from the furthest reaches of the night sky, what happens as the universe expands?
It's a profound thought.
As the cosmos stretches, the relative velocity and the wavelength of that ancient light slowly shifts. If our fundamental building blocks are entirely defined by the light they catch, then as the light of the universe changes over cosmological time, the very nature of the matter making up your bones and blood is subtly drifting along with it. We aren't just in the universe, we are an ongoing physical reflection of its changing shape. Keep looking up, and we'll catch you next time.